kör fra. Ja. God kvöld allesammans og velkommen til veðurlagsbroytingum her i Norrland husen som vi har annonserat nu några ferier och sådana delar. Och vi för att vi så ska tacka musikskolan för den fraliga tonlöjden ut i Føroyar. Och så för jag nu höjda det kon om att slutcha färdtelefoner så det här kunde öregva tekniken här inne. Och så hade jag skilt jag sig rätt att han tonlöjden eller dansen eller vad vi nu skulle kalla det som fyllde jag in här. Det var en blanding av sumpingon som hvørvur och indianer som dansar kruksdans. Heimeren han ju sera fjällbröter. Skræin jokken annars det är Siri Stenberg för att säga några år för vägna landsturen. Så gärna för Julian Dowdswell, professor at Scott Polar Research Institute at Cambridge University at halda fyrirlestur. Etter han kommer Andy Bowen, principal engineer at Woods Hole Oceanographic Institute i Massachusetts. Og søstrerøyene han som vi kjenner så vel. Føroyar Boy Hansen, havfrøyngur og havrannsøknarstovne. Spurningene tar gøyma vid til alle trutjer fyrleser halvdagen hava vere. Og annars så sier jeg at det er velkommen å ta seg vidt ut i gongene eller ut i forholdene i 18 år. Om onker ikke hva sette spurningar her inne. Tar vi det liv her så halda vi nemlig fram her ut denne løte vi leskande drikkon og en løtler hundaløte. Men først får jeg bjør her velkommen Siri Stenberg, landstyrskvinna. Du får dåre.
Ja, stora tack för det. Det var fantastiskt att komma in horna här och höra dessa fralöjtje folkene fra musikskolan och spela och inte minne heimlott att höra sumpingar kvöva där man kom vujer. Men gåa tycker ull. Först får jag tacka utlom fyrirækaron för jag har sett sjånekna och hetta alvarsmål som är bøyen till att sätta i kvöld. En särskilt tack till Hoksjonarmann och Johan Mortensen för jag har tidsi sti til dessa stævne, og for jeg har sett saman en sjálfsamma áhugaverda skra ved framlån fra alt sjåa virkjent og granskar og økjennom, både i utlandskjør, og ikke minst fra okkara fremsta veðurlagsbroytingum Boa Hansen, som i áravís hefur verið undangångu folk og hesson tutningar mikla øk. And to our honored guests from abroad, Professor Julian Dowdswell, Director of the Scott Polar Institute, and Mr. Andy Bowen from Woods Hole Oceanographic Institute, we are very pleased to welcome you to the Faroe Islands and we are grateful for your participation in this event. Virlegi kring knutton brøytost. Nottuna til okkara flaggdag var en nutj virlagsfrakring almanna kunngjord, vi så døpro nyurstuen og forsagnon at tøyndni hava løpt kvukk av Atlanheim. Og i så måte så kunne tiltaket i det ikke være mer aktuelt. Fragreingen som arktiska rai og by stedfester er hiton ved Nordpolen hekkar tvøyfalds og kjott som hiton i resten av heimdom. Hiton hever mellom annet visser at Ísurin kring Arktis brannar og nutj fragreing visser eisne at Ísurin brannar vel kjottare enn okra av hilti fyr. Eit nu brannar innlands Ísurin og grullandet fyrir kjottare nu enn han gjort i 2008, og tjej fyrir kjotar enn fyrir 20 år siden. Og forsagnar mildt sagt ørkjemland. Til vi hesare gong som metagranskar av langt ut 2030 Ísurin kring Nordpolen borstor sommar. Nyurstunar ikke nutj tøynder som så. Hetta i avværingar som har vært framme i åra tøtjur. Og tog verri hevd ikke etnast å få vent gongtene hoast avværa hevd vært dåliga. Men nu tidjust venta vera. Folk og lånt rakna vi, og åraskiftet ikke langer man skal gjøre noe, men heller hva man skal gjøre. Og suttja og kunne ekleia vi ber egen hva hentur. Hette ikke noe som bare verer ena for i framtiden, men det noe som langt nu. Jeg hugsa heiti av kvultenen om det at Ísurin brannar. Da jeg var baden i vaie, da hudde jeg Ísvestri av vattenen, og skøyta i kvunnvetur, og hudde enda skøyte kappingar. Og byrja vi treskøyton, og så kom jernskøyton her. Og ullbund åtte sparskara. Mine bøtten har omgående 8 kvurste treskøyter, eller janskøyter, eller stegi av skøyten av vattnet, til her har omgående vært frist. Og sparskaren nærmest en fotloter, og hette bare et lite, tydelig døme og kjenne ut flere. I skipet har vært sagt at de som strøyast vid torsk, de får få enda mer torska. Og til åkon, vi avstod og vekkre, vi vinter og regne, får få mer avstod vi gjør, vi enda flere stormon og enda mer regne. Så det er lite hoalott. Og i mynte tykken en heim utan kaffe, skriver jeg en fjellmil nå en dag om. Det så drekk og mer enn 2 milliarder kopper av kaffe, men nå er framlastene i Colombia, Kenya og Etiopia hatt av veðurlagsbroytingum. Jeg råkner vi at de fleste av dere kunne iverliva at dere ikke langer få hetta gerandes ritual ved kaffen, men for de som tenkt av disse framlastene, så hetta et alvarsmål. Jeg var en i alt kjøva kvinneravstøvn i fjør, og valgte jeg for at lenne verkstov om kvinner og virle. Og det var rent jeg høyre til deres omkursraheren og Nigeria greia fra hvordan veðurlagsbroytingane er mestest just til Taimon. Først mest kvinner det. Det var ter som arbeid i landbunene, og økene her til fyrhudde kunne haft landbunene var så å si av borster og blunner øyemørsker. Et av utslutene var at en stor mangd av klimaflotten flottet ikke norra klotene, men her var ønskens herlige vilje til å hjelpe. Og nok var stedene merkja menneskers sviðan av brøyta veðurland og langt nå. Ekstremar åtner etter håndene gerandes koster og krevja nok mannaløv kring heimen. Sjålsamar hitabilkjør, bare i sol og nord, ikke langer så sjålsamar. Og veðurlagsbroytingane avvirka eisen i okkara, bare helse og sjuke minster. Mittel anna så gjør broytingar av djur, insekter og planter flytta bostad, og kanskje tina undan øysenen og føra ærer smittervisser som dere ikke har kjent før. Så en fiskevinne kjøl som til åkon hever hiton i høven og avkjørende tøtning. Hiton hever avvarskan og hvordan fiskastånene ferast og hvordan omstår det til dømes for i æling. Og samståndet er det avbendingar om at goldstrømmeren kan fære viktna enda meira enn å kunne gita om og å kunne bæra gita om hvor avlengene er vera. Og veðurlagsbroytingane kunne ringast av føretaka borster tøyande grundalega under okkara boskapet og overhøver grundalega og kunne bolegast av hesson fantastiske øtjon. Og liva ui, vi og av naturen. Enn nok for avsvære spurningar til det kommer til avleggingar og veve av orsakene av veðurlagsbroytingene. Og i nevnte frakreiing vil eisne malt til å styrke granskingene, så forsagnar kunne gjørast enn betur og meira uttøkjeligere. Tog i umynd gjemmer eisne at okra raskje og tilvita i ungdommer framover for å uppbygga seg enn meira innanfor læregrenar som kunne gjøre okkur klokare av hessen ødj. Ta veri ikke til dømes innan lovfrøye, havfrøye, virle, orske, geologi og borardrikt og så framvegis. En stor parter av okra framtid kommer litt her og ligger langt i her. Flest alle granskar en normallig om at veðurlagsbroytingane mannaskaptar og at høvesorsøkjon utlatet av vaksarhusgassen. Tog kanskje mer åtråkande enn akkurat tog å få minka om utlatet. Heims samfellet må teka just i for å byrke opp fyrre brøytingene. Og alt sjå samfellet tok at tøtningar mykje fet i fjør til Paris-avtalen kom i hus, men enn manglar å få glaslige malene gjort til utøkelig atøk kring heimen. Men det tidligst nå være en vilje til å vilja gjøre noe. Føroyar vi i Paris-avtalene. Okkara loter her i Føroyar må ikke litt etter. Naturen grundarleie under føreska samfunnene, og tog et okkara skilta av være mellom til lån som kunne gange undan av omkursøkene, heller enn å kasta apert fråg. Iverskipa i Mali og kopp 1 avtalen å halda meal hita vøkstron av hjørne nirre, og at vøkstron av allheims utlaten av vaksarhusgasse skal stukka skjåtas tilber og heretter fatla skjått. Bare for åkken som nå det, men sannelig eisne for å gjøre kommande etterligen møvleika av livet vel og i som gåa landet og i som gåa heime. Håvast at einmalt lukting ut 2008 tok under ved veðurlagspolitikk fyrja, og malen om å skjerja utladet av veðurlagsgassen ved minst 20% til 2020, så gonger så som så vi har rukket som malet. Det gonger for sent. Her må sterskare luter til og myvis politisk atøk. Paris-hotmålen stig av vennen, til her har vi forpliktet til å skulle handla. Og grønne orskepolitikken til samgångene skjolan og i veðurlagspolitikken. Og skulle bort fra dolkande oljene og få folk å velge grønne orskeløsner. Og her har sett noen fyrre at helten av utlån setusen og bygningen skulle hittas ved grønne orsk innan 20 år, og at i 2030 skal utlån elorsk av landet stava fra hverandre orskekjeld. Hetta for å gjøre en stor amon. Bært nå arbeider vi hvis vi har stola og ikke folk til å lette og kunne velge grønne orskeløsner. Og lagt opp til vindorske utbyggingar sammen ved vattenpumpeverket kommande årene. Og somleis byggjer landet grunt nå og har avsett regler for bygging fra stole under malen og man kan sutja at oljeinnflutninger minkar. Så og flytokon. Brukar av sujan og framleisle sujan må ganga hånd i hånd, men og skulle teka kritikken til okon at og flytokon for sent og at stortøk i etter å teka. Vånen tå at og kunne gjerast undangang i tjå og fyrmynd for ånder innan grønne orskenusli. Og her hoalt av sutja alt det arbeid som nu eisne fyrir fram av græsrådanivå, her det ofta her hoksjonen spretta og gåen fellesskapet og i mittlun eldsaler. Og jo en broytingar tog, og jeg halte av flere av de største spurningene vera omgantøy eller hvorfall skjoldan setter. Og spurningen om forbruk. Skulle det være et forbrukarsamfella? Bruka og blekka bostor til okra mentan og samleitje. Og det en naturlov at boskapen skal veksa hvert år? Jeg spyrir bare. Og jo, og skulle menneskene, og skulle utbyggvåkene, og skulle bli klokere, men skulle ikke framhaldande være så store materielle forbrukere. Det tjekk eigra teka, og her kunne utgjøre neka. Vi har sånn åren så fer jeg innsjukken utlån godt kvult, og jeg får takka for innbjørnsene, og høver jeg til å være sammen om hvordan vi kan få litt til oppgave i fjellet. Takk for det.
Ja, vi takkar Siri Stenberg, landstyrskvinna, for velvalgt år. Vekkre og veverleie, hese årene har vi hørt, siden vi død var lusta etter utvarpen. Og 17 årene har veðurlagsbroytingar runga i ødelen heimsens fjellmilon, climate change and global warming. Sånn som nødja så rapporten fra grøngen som Sirius nevnte, svipa fra grøngen som viser at Ísurin og Arktis brannan skjótar enn hva vi genga og halda. Lat okkur en stuttum filme, dvelja vi hva vi verilig har vi gjøre her i Norrhøven. Welcome to Mr. Julian Dowdswell, Professor at Scott Polar Research Institute of Cambridge University. The floor is yours, Mr. Dowdswell.
Thank you. Thank you very much. Thank you. Minister, ladies and gentlemen, it's a great privilege to be back in the Faroe Islands, such a beautiful country, which I first visited when I came as a student aboard the Smyril in 1979. What I want to talk to you about today is ice and environmental change, and I think that that was a beautiful introductory film to what I'm going to say. But before I go on to the topic, I'd just like to say a couple of words about the place where I work, the Scott Polar Research Institute in Cambridge University. The Scott Polar Research Institute was founded almost 100 years ago as a national memorial to Captain Scott and his 4 companions, Bowers, Wilson, Oates and Evans, who died on their way back from the South Pole, and many of you will recognise the famous photograph of them taken when they arrived at the South Pole just a month after the Norwegian Roald Amundsen. So we are a national memorial to those 5 great men. But we're about more than simply the legacy of Captain Scott. We're about Britain's polar heritage more generally, first of all, and Ernest Shackleton, of course, is the other great British polar explorer that most of you have probably heard of, a picture of his famous boat journey between Elephant and South Georgia up here. But the Institute is their legacy in the sense that our main role today is to try and understand the way the polar regions work. We study both the physical sciences, the natural sciences, and the social sciences in both the Arctic and the Antarctic. And I've had the great privilege of going to many parts of each of these superb parts of the world. We teach undergraduate students in Cambridge University. We have about 40 graduate students in the Institute. And I think it's fair to say that our Polar Library, Archive, and our museum, which has about 50,000 visitors a year, a number which hasn't been lost on me in the Faroe Islands today. We have a lot of a national role in terms of public outreach. So that's just a little bit about where I'm from. But what I want to talk about today are these questions. What are glaciers and ice sheets, first of all? Why the polar regions are important? Because 40 years ago, when I started doing research, people thought that the polar regions were interesting, but they didn't really see why they related to people at lower latitudes. And now I think we do. How scientific work is carried out there? What is the modern climatic context in which the ice sheets sit? And what is the response of those ice masses to that climate? So firstly then, what are glaciers and ice sheets? And of course, coming from the subarctic, many of you will know a lot about glaciers and ice sheets already. Glaciers and ice sheets, as opposed to the frozen sea surface of sea ice, are produced by the falling of snow crystals and the fact that those snow crystals, where ice builds up, stay for the whole of the summer. This is a photograph of a glacier in Spitsbergen, firstly in winter and secondly in summer, the winter scene at the top. And what you can see is the frozen fjord, but also the mountains and the glaciers themselves are completely covered by snow. In the summer, the contrast is almost complete. The sea ice has gone, and you can see that the winter snow cover here has been replaced. All the snow has gone, and it's been replaced by the ice surface. But high up in the glacier reservoir areas, some of the snow that's fallen the previous winter remains. And it's that snow that builds up to sustain and nourish the glacier, because as it densifies, it turns from snow into ice. Now, of course, if that snow, which turns into ice, just stayed in the upper areas, the glacier would build up and up and up in that area, and this lower part would simply disappear. But it is the fact that ice flows very much like a metal near its melting point, that just enough mass is transferred from that upper accumulation area down to the lower part of the glacier to compensate for the mass that is lost. Now, if the winter inputs of snow equal the summer losses of ice, then the glacier is said to be in equilibrium with its climate. What I will show you is that very few glaciers and very few parts of the icy world in general are in equilibrium with their climate, and most are thinning and in retreat. And what I want to do is talk a little bit about the consequences of that thinning and that retreat in a warming world. Glaciers and ice sheets come in all shapes and sizes. Glaciers are surrounded by valley walls. Ice caps, such as this one in eastern Svalbard, which is the biggest in the whole of the Eurasian Arctic, are ice caps. And ice caps conventionally are thousands of square kilometres in area, whereas the two great ice sheets of Antarctica and Greenland are millions of square kilometres in area and thousands of metres in thickness. So the first part of the icy world are the glaciers and ice sheets, which are built up from the densification of snow into ice. The second part is the frozen sea surface. This is the sea ice that forms in winter over millions of square kilometres around the Antarctic and the Arctic seas. And the third component of the icy world, and probably the least well known, is that of permafrost. And permafrost is permanently frozen ground. A layer about a metre thick melts in the summer, but below that are vast ice bodies. You can see that much of Russian Siberia and the Canadian Arctic islands are composed of permafrost. And of course, if permafrost melts, a lot of organic matter is contained in it, and there is a danger of substantial methane release from processes such as those. So why then are the polar regions important to those of us who live, and the bulk of the population of the world, who live at lower latitudes? The first reason is because water from the global ocean and from the open hydrological system is stored in the glaciers and ice sheets of the world. Therefore, if glaciers melt, that water flows back into the global ocean and sea level rises. And this matters to coastal communities throughout the world. It is a global problem. Secondly, sea ice, the frozen sea surface, and you can see sea ice forming offshore of Greenland in these little pancakes. Sea ice, as it forms, as the sea surface freezes, rejects salt. And the water that's formed when sea ice freezes is the saltiest and densest anywhere in the world. That water sinks to the base of the water column at depth and, in the northern hemisphere, flows south. The return flow, in our case known as the Gulf Stream, the upper 800 or 1,000 metres of the water column, which keeps Britain, the Faroe Islands and Spitsbergen the warmest places for their latitude anywhere in the world, that flow is stimulated, in part at least, by the formation of sea ice and that dense bottom water. So what sea ice does affects the global ocean circulation and therefore all of our climates. The third reason why we want to know about the polar regions is because actually quite a lot of people live and work there. And I don't only mean the Inuit, and I thought the Inuit image at the beginning was a very, very beautiful one. I don't just mean the Inuit, I mean also people who live, like Russians in the Svalbard archipelago, and remember about 1 million Russians actually live in Siberia, which is part of the Arctic itself. And of course, there is the thought that major shipping routes may emerge as the sea ice concentrations in particular decline. And then, of course, let us not pretend that there aren't national interests in the Arctic and indeed the Antarctic. The scientific activity, and I deliberately put a British flag and a New Zealand flag up here because these are the territorial claims to parts of Antarctica that are simply held in abeyance under the Antarctic Treaty. So science and geopolitics really go hand in hand in the Antarctic and to some extent in the Arctic too. And finally, and I put this in because I'm interested in it personally, we want to understand the landscapes in which we live. The Faroes, of course, has been glaciated just as upland Britain has been. And if we understand the behaviour of glaciers such as these in Greenland, we can understand the formation of our own landscape. How do we carry out scientific work in the polar regions? Andy, as an engineer, is going to tell us more about this, but I just want to show you a couple of things. This is from the British exploration of the Northwest Passage, north of Canada, in the 1840s. And for those of you who can't see this, it's called The Pursuit of Science Under Difficulties. And what this man is trying to do in the polar night is take meteorological readings from a little table offshore of a ship. And you can see he's come across a polar bear. And what it says is his situation, to say the least of it, was not an enviable one. For one spring of the brute, the bear, would have put an end to his registering of thermometers forever. Of course, it's not quite like that, and it's not quite like the days of Captain Scott and the rations that they ate 100 years ago today. But equally, when we do field work on the glaciers and ice sheets themselves, a tent is still a tent, a blizzard is still a blizzard, and if we forget to stick our skis up like this, we will spend 3 hours looking for them. That sort of thing hasn't changed. And this beautiful Edward Wilson painting from Scott's last expedition, I think encapsulates, compared with this modern picture from Spitsbergen, that when you're camping in the polar regions, things are not so different as they once were. But of course, for the most part, we use geophysical research vessels. This is a British one, the James Clark Ross, which from time to time I know has been through the sounds and passages of the Faroe Islands. Andy will tell us much more about autonomous underwater vehicles, such as the little yellow submarine, as we like to call it, just down there, which we can put instrument packages on. We use radar systems to measure the thickness of ice, because ice is semi-transparent to radio waves at megahertz frequencies. And this is a very useful civilian purpose, to use a Russian military-equipped helicopter. The missile mounts here are being used for the friendly purpose of our radar measuring the thickness of the ice. And then, of course, we use satellite views of the world very extensively, and these are images of the breakup of the Larsen ice shelf in Antarctica, which occurred very abruptly about 15 years ago, and was one of the real signs that the Antarctic continent is affected by climate change. And then finally, the ice sheets are a fantastic repository for past climates. The layer on layer on layer of snow that is built up and densifies into glacier ice gives us a fantastic history running back, in the case of the Greenland ice sheet, about 100,000 years, and in the case of the Antarctic ice sheet, at least 800,000 years of Earth history are encapsulated in the record from ice cores. But what then is the modern climatic context in which glaciers and ice sheets sit? This is a record since 1850 of the global mean temperature. And you can see the 19th century was colder than the 20th, and particularly since the 1980s, we have had a large increase in temperature. And you can see that 2015 and 2016 are both the two warmest years on record. And if we compare the 1960 to 1990 period, this one here, with the period since, we find that the temperature has warmed by about 3/4 of a degree over that period. And of course, a question that we're often asked as scientists is this a natural change, or is it human-induced? Is it anthropogenic? And this little diagram, I hope, explains a little bit of why we think it's a combination of the two. This is, in red, the observations of temperature change since 1850. The grey line in each case is a computer model simulating the way that the environment has changed. And we then compare the computer model, the grey, with the red. Now, in the first case, because it's a computer model, we can actually pretend that there has been no increase in greenhouse gases, human-induced. And we say we will suppress those changes, and we will just model the natural changes. That is, solar radiation variations and variations in dust, particularly volcanic dust in the atmosphere. And what you see is the fit between the observations and the model is pretty good for the early period, but pretty bad for the period since about 1980 or 1990. Similarly, we can do the opposite, and we can pretend that there have been no natural changes, and we just say we will just use the greenhouse gases and sulfates, the human-induced element. And here we find the fit is very poor for this middle period, but very good for the earlier period and the modern period. And of course, the message from this is quite clear that what we want to the way we want to understand the climate system is to include both the natural changes, the solar and the volcanic, and the human-induced changes. And when we include all of those things, we find that the fit of the model with the observations is very good. What that tells us is that natural changes, of course, continue, but that human-induced changes have been very, very important over the last 30 or 40 years in particular. So it's a combination of the two. And if you ask me, as I'm sure you will afterwards, what the combination of the two is and which is the more important, my own view is probably that 60 to perhaps 80% of the changes that we see are a result of human greenhouse gases, sulfates, and the like. Now, let us return to the Arctic. The Arctic is arguably the most sensitive part of the global climate system. For any numerical model that is run on future climates, the Arctic always comes out to warm more than any other part of the globe. Why is that? The answer is complex and yet simple in a certain way. That is to say, what we are doing by warming the Arctic, and remember the Arctic Ocean is a huge area covered by a very thin, few meters thick sea ice cover. That sea ice cover is white and very, very reflective. If the temperature in the Arctic rises slightly, a little bit less sea ice is produced, a little bit more dark open water, which is very much more absorbent of incoming radiation. More of that is present, and therefore the sea warms a little bit more. And then the next year, the next winter, when the sea ice starts to form again, that water is a little bit warmer, a little bit less sea ice forms, a bit more open water is present, and so on and so on. And this is what we call a self-reinforcing process. And this is why in absolutely all the models, whichever group's models you use, the Arctic is seen as the most sensitive part of the global climate system. And it is thought that warming in the Arctic may be somewhere near double what the global average is. And of course, since so much ice sits in these areas, this is very serious for the icy world. So, what is the glacier, sea ice, and ice sheet response to this warming? Firstly, sea ice. This is the satellite-derived observations of the whole of the Arctic in September from the first satellite data sets in 1978. So we have almost a 40-year record. And we can see that although there is a lot of interannual variability, you can see, and these are big numbers on the left, you can see that from between 7 or 8 million square kilometers of ice at the end of the summer in the 1970s and 1980s, we are today down at a number that is at best 2/3 and sometimes, in some years, almost half of that number. So in 40 years, the amount of sea ice cover left at the end of the summer is somewhere near 1/3 or 2/3 or a half of what it was 40 years ago. And I've just inserted the 2016 measurement here. This is an enormous change, and this, again, is the main reason ice albedo, ice reflectance feedback, self-reinforcing process, why the Arctic is the most sensitive part of the climate system. Why is it important? These are a few of the examples. If there is little summer sea ice left by whether the number is 2030 or 2040, we're not sure, but what it means is the Arctic and the high Arctic will be much more accessible for shipping, for industry. It is arguable that many more ships will go through the Northwest Passage across the top of Canada because it's a quick route between the Pacific and the Atlantic, and more traffic, and indeed it's easier really to go through the Northern Sea route north of Russia too, in this situation of declining summer sea ice. And of course, this also poses problems for the biota, for the animals that live in the Arctic, because they often rely on sea ice for hunting and where they live. And this is a photograph that I took just a couple of years ago in the Barents Sea, east of the Svalbard archipelago. When I first worked in this area about 30 years ago, it was covered in really heavy sea ice right until the late summer. Now, not a sea ice flow to be seen. In fact, what we can see here is a rather sad and distressed polar bear, which is basically, and not to put too fine a point on it, swimming for its life. And that is the reality of the situation in some parts of the Arctic today. What about the glaciers and the ice sheets and their links to global sea level? This is a beautiful painting by an artist who went on Prince Albert I of Monaco's expedition to Spitsbergen just about 100 years ago. Not only is it a beautiful painting, it's also a very accurate painting of what is going on. A ship for scale, but note the shape of the mountains, the debris, and the little moraine ridge at the side of the glacier, and also the joining of the two glaciers here. I went back to the same place almost exactly 100 years later, and this is what we see. The ridge that is here is now this ridge. This is the splay of debris. The place where the glaciers joined, the glaciers no longer join. And we can use historic information like this to go back beyond the early observations from satellites to see the changes that have gone on longer timescales, the timescale of 100 or 120 years. So this is a qualitative observation of thinning and retreat, which is quite dramatic. If we go to the Great Ice Sheet of Greenland, a near neighbour of yours here, we can see from satellite evidence now the difference between the amount of melting on the ice sheet margin in 1992 as compared with 2002. And if I had 2007 up here, we would find that the red, the area of melting, would be almost completely covering the Greenland ice sheet. And that water runs off back to the global ocean to raise global sea level. The beautiful film that we saw at the beginning is of the same area as this photograph. You recognize the kind of terrain. This is the ice front. These fast-flowing glaciers, which drain, about 10 of them drain almost the whole of the Greenland ice sheet. They're huge glaciers. They were flowing before about the year 2000 at about 5 or 6 kilometers per year. Since the turn of the 21st century, they have almost doubled in their speed, and they're now flowing at 11, 12, or 13 kilometers per year. And the icebergs that you saw in the wonderful film are now contributing to global sea level rise, and the mass that is being lost from this ice sheet is hugely greater than it was even 2 decades ago. The melting is not just confined to the polar regions. We sometimes call the high altitude areas of the world the third pole. They're cold, therefore we caricature them as polar, but they're of course altitude replacing latitude in stimulating the cold. This is a picture, a satellite image of the northern Patagonian ice field. It's about 4,000 square kilometers in area, so bigger than the whole of the Faroe Islands. And this glacier has been thinning at about 2 meters per year. This is an enormously rapid rate. So the high altitude glaciers of the Himalayas and the Andes are also contributing water back to the global ocean. Antarctica is a slightly special case because it is surrounded by an ocean which to some extent slows the movement of heat from lower latitudes to high latitudes. So the Antarctic is a little bit isolated from the rest of the global climate system. We can divide it into 3 parts. The huge East Antarctica, separated from the smaller West Antarctica by the Transantarctic mountain chain, and then the third area, the Antarctic Peninsula, which sticks up towards South America. The Antarctic Peninsula is suffering from glacier thinning and retreat the most, and this is a diagram of the vast number of glaciers that are retreating along the western margin of the Antarctic Peninsula relative to those that are advancing. Similarly, if we look at the West and East Antarctic ice sheets and we monitor through satellites and the changing elevation of the surfaces here, we can see that the reds and the oranges show that West Antarctica is thinning, and indeed the ice is retreating there, but East Antarctic, the biggest ice sheet in the world, is relatively stable at the moment. What does all this mean then, all these changes in the glaciers and ice sheet? What does this mean for global sea level? Sea level is controlled at the timescales that we, our children and our grandchildren are interested in, that is decades to centuries, by two things. Basically, thermal expansion. That is to say, if I heat a glass of water, the water will expand. If we heat the global oceans expand. And that accounts for a certain amount of sea level rise today in a warming world. The other big contributor to sea level rise today is the melting and the thinning of glaciers and ice sheets. These are the two main elements, and both of them, you can see, are a function of climate warming of the globe. And this is what sea level is doing. This is changing sea level in millimeters from the 1990s until today. And what you can see is today, the rate of sea level rise is almost 3.5 millimeters per year, whereas the average for the 20th century was a little less than 2 millimeters per year. So sea level rise post the end of the 20th century is getting on for double what it was during the previous century. So sea level is rising and is likely to continue to rise at an increasing rate. And if we look at just a couple more graphs here, the first one is a prediction of future global average temperature. And on the right here, you can see a number of scenarios for the way that humankind may influence the amount of greenhouse gases during the 21st century. The first one is such a low future input scenario, I can't even fly home. I have to walk back from the Faroe Islands if we're to have an atmospheric future like this. It's not going to happen. The very high one may not happen either. So we're probably somewhere in the middle for the 21st century, which means that the global average temperature is likely to rise between, let's say, perhaps about 3.5 degrees centigrade. And remember what we've said about the sensitivity of the Arctic, that the Arctic is therefore likely to rise in temperature by perhaps 5, 6, or even more degrees centigrade over the coming century. And that is a very big number. What is likely to happen to sea ice in the Arctic under these different climate scenarios? Basically, this particular set of models suggests that by about halfway through the 21st century, there will be little sea ice left in the Arctic during summer. There will still be sea ice produced during the winter, but all of it will be gone by the summer. Now, whether that happens in 2030, 2040, 2050, 2060 is difficult to say, but it is likely to happen round about mid-century. And what are the consequences for global sea level? Here again, we have sea level, this time in meters, and we've got the 21st century along the bottom. We've got the same climate change scenarios, the most conservative and unlikely one here, and we can see that by this set of predictions, sea level is likely to rise by between about 0.5 and 1 meter over the 21st century. Of that, about 1/4 to 1/3 is likely to be a response to thermal expansion, the warming of the oceans themselves. The rest is likely to be coming from the great ice sheets, firstly of Greenland, perhaps later of Antarctica, and also the glaciers and ice sheets of the other parts of the world. For a sea level rise of 1 meter, over 2 million square kilometers of land will be lost. The biggest losers are going to be the huge mega deltas, the very flat deltas of places like the Ganges, the Brahmaputra, and the Mekong in the Far East. And there, the most land is likely to be lost. But places like Florida in North America will be very much affected. And of course, the responses of humankind to these changes in sea level will be very different, dependent on the means of different peoples to respond. This is the City of London, and this is the Thames Barrier on a day when it's open. We already are closing the Thames Barrier far more often than we were when it was first built. We have plans to add another 35 to 40 centimetres to it, and we have outline plans which will be instigated over the coming decades to completely renew the sea defences of the southeast of England, because it has been recognised that it is much cheaper, although still hugely expensive, for us to build new sea defences than to risk the inundation and the loss of life and disruption that would result from the inundation of London in some huge storm surge. But of course, that option is not open to many of the peoples of Eastern Asia. Now, the last slide, I wasn't going to put in, but I thought it might amuse you. This is what would happen, and remember, it's not very likely to happen on any time scale that we were interested in. This is what happens if the whole of the Antarctic ice sheet were to melt. Sea level would rise by about 60 metres. This is tens of thousands of years away, so it's not in anything that we need to worry about. But I thought the thing that would amuse you was this bit here, because everything blue will be under the sea. Thank you very much. Thank you.
Thank you very much, Julian. Thank you very much, Julian Dowdswell. And from Cambridge University to Woods Hole Oceanographic Institute, Massachusetts, our guest from Woods Hole, who has come to share his many years of experience with us, is Mr. Andy Bowen. He's a principal engineer at Woods Hole Oceanographic Institute. Welcome to you, Andy.
Thank you very much. Thank you very much. This is a real pleasure to be here. I'm a technologist and engineer at the Oceanographic Institution in Woods Hole, Massachusetts. And what I'm going to do is talk a little bit about some history that has driven innovation in the development of systems that provide access into the ocean, tell you a little bit about what the state of the art is, explain some work that we've done to reach the more extreme parts of the ocean planet and some of the technology that's been associated with that, and then try to relate it to some of the questions and challenges that we've just been hearing about relating to polar research. I call it the tale of two tethers, and this title might become clearer as we go further along, but it's really about the way we interact with our robot systems, and tethering, whether it's virtual or physical, is an important part of how we as humans interact with our mechanized robots. Before I get too far into it, I'd like to just give you a little bit of background about Woods Hole Oceanographic Institution. It's the world's largest private nonprofit organization involved in basic ocean research. We have 450 engineers and scientists, budget a little bit over $200 million a year. Most of that comes from the federal government in the United States. But really the key goal of all of that is to basically uncover and try and understand the natural phenomena relating to the global ocean. And that is in each one of the basic disciplines, so biology, physics, chemistry, geology. And then there are those of us that are the engineers and tool makers that provide the access into the deep ocean environment. The idea of why robotics in the ocean is important, really, I don't have to tell you, you are all very much an ocean nation and very aware of your surroundings. It's a harsh environment, and while there are certain things that humans must do at sea, having automated systems, robots are quite valuable. They give you larger access, more safely in some instances, reduce costs, and basically are an effective way of conducting operations in the ocean. Woods Hole has really led in this area. These are some sort of applications. I'll maybe talk a little bit more about some of the details. We're fairly well known for discovering the Titanic and exploring it in the 1980s. More recently, we've used some of the robotic technology to do some challenging enterprises or exercises in locating, for example, a lost airliner, or on the right-hand side, also exploring or trying to learn more in response to the Gulf of Mexico Macondo incident. This one of the stimulating sort of events, I suppose you could say, that's relevant to the story I'm telling you today, sort of is represented by this slide. In the 1960s, there were several notable instances where submarines were lost. Some of them belonged to the United States, some of them belonged to Russia. The Cold War, of course, was raging in those days. And really, the state of the art in those days was to sort of climb inside a steel ball, as Beebe and Barton did. Now, this is in the 1920s, but still generally represents kind of the state of the art. And, basically go to the deepest part of the ocean, but all you could do when you got there was to turn on your flashlight and look around. And that really turned out to really obviously be a fairly limited way of really exploring the ocean. There was no way to sort of see beyond the headlights. And that really was a limitation, particularly with regard to finding and locating some of these objects on the seafloor. And so a young member of Woods Hole's staff, Bob Ballard, is pictured here, started his career as a geologist and was, I guess you could call, sort of unconventional and maybe a maverick, and was thrown out of the geology department and became part of our department. He had a long-standing involvement early in his career with the U.S. Navy, and was really someone that I think led the development of technologies to provide that much larger access to the ocean, and came up with this concept called Argo-Jason. And so, as you can see on the left-hand side, the image here basically shows a ship with a multi-beam sonar, and up until this time, that was essentially all you could really do. But each one of these footprints gave you an average depth for something the size of a football pitch, which might be good for mapping very large features on the seafloor, but it was not very adequate for finding objects or mapping the seafloor in sufficient detail. And given the physics of the way sound travels in the ocean at very deep depths, you really needed to actually bring something down to the seafloor, and the concept was the development of this tool, which provided you with sort of eyes and ears very close to the seafloor. And this is an early version of it, sort of almost a caricature of the robot. The idea that this, as I was saying, brought the information to the surface in high enough resolution so that you could sort of make these discoveries and maps of the seafloor, and then even beam it off the ship and send it to shore where it would be accessible to a larger number of people. And this was the vision. So we embarked, this is in the early 1980s, on the sort of technology development part of this project. And the first part of that that I became involved with when I came to Woods Hole was the idea that we were going to develop this little robot that could go down into the deep ocean. It would sort of be the first part of the Argo-Jason system that I showed a minute ago, but instead of having a cable that went all the way to the surface, which didn't really exist in those days, what we did instead was to attach it to our small little miniature 3-person submarine. and take it down to the deepest part, or not deepest part, but to a deep part of the ocean. And in this case, it was used to inspect Titanic, and this painting shows Alvin having landed on the deck of the ship and then dispensed the little robot inside the vessel. The Navy, of course, was interested in this type of technology, and it was used, not surprisingly, to actually investigate some of the wrecks of sort of naval importance as well. You know, the sort of young team that was assembled to work on this, and our robot pictured here, you know, was a group of individuals who were, you know, highly motivated. We had a great leader. We were well funded. It was a really exciting ride. And sort of, this is leaping forward now many years, but this is sort of the ecosystem of robotic systems that have sort of emerged, I suppose. You know, here at the bottom of the tree would be the Alvin system, which still continues to operate today, actually, and has just completed an overhaul and an upgrade to its capabilities. The Jason Jr. robot, these two elements, the human element tethered to the robot, sort of have bifurcated into these two elements of the family tree. So here you have what are termed autonomous systems. So unlike the tethered vehicles, the robots that are tethered to the ship, where they're supplied by energy through that tether cable, and the pilot actually controls the actions of the vehicle through that umbilical cable. This side of the tree actually are untethered, and so they have a battery on board, they have a computer, they have communications, and they perform a mission that you load into the robot, and typically that's used for the purposes of mapping. And then on this side we have the tethered vehicles, the original Jason tethered vehicle you saw a photograph of, and then the larger Jason vehicle. And I'll talk about this in just a minute, which is sort of the fusion of the two of these. The Jason ROV, which you saw earlier, has you know, become a valuable tool. So that photograph was taken in the late 1980s. This one was taken within the last year or so. Jason's gone from weighing 2,000 kilograms to nearly 5,000 kilograms. It has two very capable mechanical arms, a range of cameras and sensors, and it's really a valuable tool for performing science in the deep ocean with a variety of capabilities, and is used pretty routinely today. In parallel with the development of the tethered vehicles, the autonomous vehicles have likewise improved in their capability, and this is a series of images that sort of show some of the work that was done by an autonomous vehicle in searching for the Air France airliner that was lost during its trip between Brazil and Europe, and which for quite some time was not successfully located, and we were asked to use some of our capabilities to sort of supplement, I suppose, the commercial work that was going on to try and search for this airliner, where we used the AUVs to map the seafloor. So the kind of mission that I described, where they're loaded up with a path that they have to perform, they gather side scan information, and ultimately were successful in locating the airliner in the deep water. So the idea that we have these two tools, tethered vehicles and autonomous vehicles, actually was something that we wanted to combine together into a single platform and build in such a way that it could reach the very deepest part of the ocean, which is in the Western Pacific. It's the so-called Mariana Trench. And there was a significant amount of interest in actually building a vehicle that could go 7 miles or 10 kilometers deep in the ocean, but to enable it to actually perform the sort of survey mission that you saw typical of searching with side scans and cameras and so forth. But instead of bringing another vehicle down to actually interact or draw samples, this vehicle could be converted into a sort of version of a remotely operated vehicle with a mechanical arm and actually perform this mission. Relevant to the idea of exploring the poles, for reasons you'll see, I think, in just a minute, what we wanted to do was to basically reduce the size and the scale of the footprint of the vehicle to reduce its cost and improve its maneuverability and access. And so instead of using heavy, large, steel-reinforced umbilicals that were typically used for vehicles that reached less deep into the ocean, we chose instead to use a single optical fiber. So this vehicle carries its own batteries on board, and in fact had a unique system that basically had one of these dispensers. So inside this object, there are 20 kilometers of glass fiber, as shown here in comparison to a human hair. So we'd have one of these dispensers here near the surface ship and one attached to the vehicle, and they would separate, and the vehicle would continue all the way to the seafloor and
Pick it up the bottom.
reach the bottom.
0.8 meters
And
off
this is
on
the sort of moment in that vehicle's history and our sort of odyssey, I suppose, of discovery, where we actually got to the deepest part of the world's oceans, basically.
Okay, preparing to drop the weight. Descent weight. Port descent weight motor. Okay, on bottom. Depth is 10,895.7.
10,895 meters,
Oh, yeah, I see it.
quite deep. I can tell you from my own personal experience during that time, I spent a lot of time with my ears covered and not really knowing whether we were going to make it. Remembering, of course, that the vehicle was tethered to the ship using that very, very slender glass fiber. So somewhat counterintuitive, the system actually reached its objective and was able to take a range of samples in the deep ocean. A high-risk endeavor, however, and Nereus, unfortunately, several years later was lost during a scientific expedition. The vehicle is shown here. Actually, we believe, although we don't know for sure, actually suffered a catastrophic implosion. So the design was made in such a way that we used ceramics instead of titanium for flotation and containing the electronics. All we got back from our robot was a few pieces of plastic on the surface. And that was a sobering moment. But working in the ocean is a contact sport. It's not for the faint of heart. You have to be willing to take risks, to learn your lessons, and to use those lessons to continue to take risks and do important and valuable things. In any case, we I think learned a great deal from this particular incident. The legacy, as sort of I've tried to document here, is that there actually were some innovative technologies. The tether cable I spent some time talking about, is a key part of that, but some other aspects that I think are likewise important. And so what we've now done recently with funding from the National Science Foundation is that we've taken this vehicle and instead configured it for a mission that is relevant to polar exploration. So instead of having our tether cable, the glass fiber that I showed you a moment ago, stretching all the way down to hadal depths, what we've done is to use that fiber to provide a high degree of maneuverability from the icebreaker, which I think you can appreciate. Certainly an icebreaker is a great way of reaching high latitudes, but because of the nature of ice, there are certain restrictions on the way the ship can be maneuvered, and having a very flexible long tether cable is quite valuable to providing access, as sort of shown in this particular rendering. And you could reasonably ask, why could you not program a robot to perform this mission without any tether cable? In other words, place it under the sea ice and have it perform some mission of discovery. And I think the key thing to point out, perhaps, is the fact that robots are very good at doing what you tell them to do, but they're not necessarily very good at doing what you want them to do. And there's a rather important but subtle difference between those two things. You want to make discoveries about the polar environment, as we heard in Julian's presentation. There's much to learn. There are many measurements to make, but automating that process is not a successful strategy when you know very little about the environment. And I think it's fair to say that that's really the case when it comes to the poles. So we used the so-called Nereid vehicle in its first deployment from the German icebreaker, the Polar Stern, where the vehicle left from Tromsø, Norway, or the ship did, with the vehicle on board. It was a multi-scale project, and the vehicle was deployed for that under ice mission. Some of the things that the Nereid learned had to do with mapping the thickness of the ice, looking at the biological communities, sampling those communities, and really providing researchers for the first time clear access into the under ice environment that really is not possible using conventional technologies. A normal robot with a fairly limited tether cable basically can only range a few hundred meters from the ship, and by the time an icebreaker is maneuvered into position, you've stirred up the environment and basically can't make subtle measurements relating to the sort of ecosystem that exists under the ice. And we've heard good reasons for why making such measurements really are important, particularly when it comes to the point of actually observing change and making predictions about what the outcome of those changes might be. You know, the emphasis that I made on the sort of undiscovered and the idea of the human operator is again a critical aspect to this sort of exploration that a vehicle of this type is capable of actually performing. You know, maneuvering a vehicle without the benefit of a human operator and the scientists working together and providing a real-time view of the under ice environment, it's very difficult to imagine some of these observations actually being made, and the concept that you could take very careful, focused, specific measurements using such a system likewise would be hard to automate to a level that would provide the kind of insights. Again, making discoveries about things that have never ever been seen before. 2 years later, the Nereid vehicle was used again to actually work, instead of under the sea ice, to work on the sea floor. The same characteristic, the use of this tether cable, is likewise just as valuable for sort of surveys of the seafloor. And the scientific interest in such environments is significant. Although often cruises to high latitudes with icebreakers the size of the Polar Stern are multidisciplinary, so they have physics and biology and chemistry, geology, all components combined together into a single field deployment. Part of what was hoped to discover with the Nereid vehicle is actually hydrothermal activity on the seafloor. So this would be where hot water is being expelled from the seafloor and is associated with the presence of new forms of life. These have been witnessed, typically associated with the mid-ocean ridge systems, but never observed under a polar ice cover. So understanding the nature and the relation of these communities spatially was a key objective. Unfortunately, we were basically unable to actually achieve that. However, in other words, we were unsuccessful in locating a hydrothermal vent, but there were some significant discoveries made with regard to some of the biology on the seafloor, as well as the chemistry of the water being emitted from the seamount that is, I think, leading to better understanding of the polar benthic environment. And finally, I'd just like to leave you with some thoughts. This is a rendering of kind of a technological ecosystem that is, built around some of the technology that I've been describing. The idea that you have autonomous systems operating, interacting with fixed observing nodes in a high latitude polar environment. You might have these systems actually docking onto garages that provide power or recharge. They can also extract data from the robot and transmit it back either to a surface vessel and therefore to shore. The concept of hybrid systems that can be deployed in response to certain incidents. I think that the key is some of the points that I've tried to hear, adapting the behaviors and retasking. This all involves the idea that you have robots that you can communicate with. I think that in the future we'll see the robots being more capable of doing what we want them to do, which means we can communicate with less frequency. They can process information on board. They can take that and distill it down and only communicate small amounts, because communicating underwater is based primarily just on and dashes associated with sonar. There's no Wi-Fi. There's no GPS. So basically, it's very difficult to communicate, and you don't generally know where you are. And those are huge challenges to achieving things such as, sort of an internet of things underwater. We're becoming much more, I think, accustomed to the influence of automation in our everyday life. It relies off infrastructure that just doesn't exist underwater, but it will come. And really, I think it's, the last, for polar science in particular, or for high latitudes, it's a critically important technology. This idea of having a more distributed network of capability to work in high latitudes. And it will influence understanding and I think in turn be an important contribution to the technology that's necessary to understand the world's oceans. So that's my sort of final thought. Thank you very much. Thank you.
Thank you very much, Andy Bowen, a voice from Woodsole Oceanographic Institute. Thank you very much. Ja, så takker vi den siste fyrleseren, og det Boje Hansen. Han sitter her ongstennes. Sier vel, Boje, han kjenner vidt. Velkommen.
Takk for det. Viskar det her? Ja, ok. Ja, tid sikkert må Og nekva tog som atleimer å sia, långa sagt. Faktisk alltid at Siri sier nekva tog som atleimer bedre enn jeg selv kan si det. Men jeg har også nekra mynter. Og jeg skal røyne å gjøre kjøttet av. Jeg skal ta så om hvordan færre veðurlagsbroytingum reka Føroyar. Men jeg husker jeg lykke først å spåle en lydsynder ut. Hva det vi tar så om? Altså, gjøren i fyr vi at hittna. Tog at vi mennesker har lært en rikve av CO2, koldioxid, eller hva de kallar det. Og under så kallar jeg vakstrarhusgass ut i luftene. De virker på samme måte som glasjøen, vakstrarhuset, eller som isoleringen, bjølvingen og en husen. Så etter alle sånne fornuft åtte de at hita hjørne. På samme måte som en i hus hittene tar de bjølva de mer. Hver kommer dette fra? Hver vi brenner olje, kål og gass i fabrikken, bilen, det kommer reisende fra skoarhøtting. Og utslitet så vi at inneholdet av CO2, koldioxid, og i luftene vekser, ja, det vekser faktisk bare kjøttere og kjøttere. Vi begynte å mate og i holdt trusjen noen enafor, la innehalt bant omanfor 300 millioner parter. Det var det langt vokse. Julian tog seg om Ísuringar i Arktis, med den andre han vita vid at de seneste 800.000 årene hever inneholdt teoria synder opp og nier, men til øyelige skjoltan færre opp om 240 millioner parter. Så langt tar vi begynte ta i oltrusjonen var det økt av synder og færre opp om 300, og nå det færre opp om 400, og det bare spiller opp etter. Så ja, gjør en 80 at hittene, og gjør en hittene. Det i det ikke noe ordentlig i om det. Man begynte at mata reglige einafor i 1800-tallet, og her sent i 1800-tallet kan man si, hei, man finner ikke så nekvar matestøyer kring i heimen, at det blir til at gjøre noe som en mial hita fyre alle hjørene hvert år. Altså, de tar simpelthen alle som matestøyene og råkner som mial ut for alle flætene av landet og havet. Så her en stapper for hvert år. Og som Julian jo nevnte, så skal man skilja hetta, så må man ta vita vid det, det ser man vi hittar etter klimamodellen, så må man sørge det som en sammanrenning i middel naturliga broytingar, særlig her i første parti av tojarskeinen, og så tar broytingar som kommer fra mennesken, det vi kallar anthropogenic og enskån. Særlig hesebæg i senaste årene, 2015 og 2016 har vært øyelig heit, men det helt naturligt. Det kommer i stora mån fra El Niño, og vi skulle ikke råkna vi at de neste årene være lykka heit. Men hatt det bare kommet om man har en opphiting som vart i en holdt 30 år. Og den opphitingen, hon ikke naturlig. Hon stavar fra CO2 og øren vakstrarhusgasser fra feltet. Så gjøren vi har hita gjørene omlai et sti, så vi begynte at avvarska luftene uten av kolveltingen i ene for 16-18-tallet. Og derfor halda fram, ikke så leis at hvert eneste år endelig har vært heitere enn år 4, Vi er sinter opp og nye, men i langere tog jeg skal for hjørne hittene, hvordan negv, det valgtes alt, hvordan negv CO2 og andre evne vidt kører ut i luftene, og annet som vidt mennesker gjør til. Det som avgjør hvordan heit hjørne i enden av hese røldene. Og her negv annet som fylger vi, negv andre veðurlagsbroytingum, hitabilder, til at det blir ekstremt heit i en tøy og av som støven. Faktisk være det støv i heimen som helst ikke være livande. Simpelthen tøy at det blir for heit. Og det blir mer torsker av visse støven. Helt einfalt tøy at hiten får mer vattnet fordampa ur hjørne. Og det særlig at de støven som framan undan langt har torsk, som til dømes parten av Afrika. Og den veten som ferden oppe i luftene fra hjørne og fra haven, hun regner som nere omkring ærestene, og vi får mer vannflår, globala regn. Vi får helst herere tropiske ødner, som tann i rakte Florida, Katrina, var ikke det om det. Vi får fløende hav, alt i alt en rikva av veðurlagsbroytingum allan heimen, tíðanverri, man kan si at det bedre ganske fri opp, men det har vært særlig at han fatter ikke pastoren av heimen som vil rakter menningarlandene, de kanskje som har minst, de som har lært mest CO2 ut i luften, de som har lært minst CO2 ut i luften, det har vært særlig at de som vil rakte av sånn her. Og hvordan så vi okko? Ja, hikker man bare sinte lestlig etter det, så kom det faktisk se ut som at vi er nok så heldige. Men, her er det men, vi lever i en egentlig særlig parti av heimen. Her rundt i Alysa vi hesar myndene som viser mye hitan imsa stene i haven og mye over alt året. Her i tropen, her har vi heitan skjegg, heter reia, og vi pålaner her har vi sjående kaldere skjegg. Hvis vi bruker 5 hitasti som marsk, så synes jeg dit at her er sikre halve, her konger marsk, fylker disse reielinjene. Her i Nord-Kyrrahavet, her ligger det her. Og i Bamoføren ligger det nærmere ekvator enn trus brettersti. Men for at det så inn i okkara øtje, og i Nord-Atlantshavet, så får de negv langer. Onga ærestene finner vi så heitan skjegg, så lengt bort fra ekvator, som i okkara øtje, bant her som Føroyar ligger. Og det er ja, for en part tror jeg vi har at vinteren som oftast for heita luftlokkere, ikke tatt det høyt, men som oftast har lukket, og særlig tror jeg at streimene i havnen fører heitan skjegg til okkara, det som vi vanlige kallar golfstrem. Og det kan jeg det som er atleia tåsa syndrom. Tog til det når vi har arbeidet vi på havstående. Vi har en grein av heitan skjegg som fer mittlen Føroyar og Hetland, sundan for okkon. Og vi har en æra grein som fer norran for Føroyar. Det gjør at førse landgrunneren og Føroyar er alla togene omgyrtar av heitan skjegg. Og hessen heite skjeggfren helter du i kalta sjån om borstere. Det kommer en streimer av kalton skjeggf, sur etter hendave, og ester etter mål i okkon, dette var nevnt han ester-uslenske streimeren. Men han var hilden borstere av to heita streimen som renner norranfor Føroyar. Men hessen heite streimer er egentlig nær knuttret veverland. Det er faktisk det som driver disse streimene, det er at luften her norranfyre køler skjekven nyer så han søkker, han fer ut og i nekra, og nutje skjekver ver sågen norretter. Men det gjør så samstundes til at ta jeg nå gjør en hittnar, og som Julian nevnte, så hittnar poløkene, eller Arktis særlig nekv, ja, så en vante for at hese streiman likna. Det har vi vita lunch. Og det en grunn til at vi har rønt å fylja vi. Vi har herstående matemaner nå i 21 år. Og her ingen brøyting. Her det, hvordan sier, ikke visse ekvelige konstanter. Og det sjående det gledelig. Men vi skulle minnes til at fyrbils har vi bare se byrjanin av veðurlagsbroytingum. Halda fram og terfæra utan i være nega velmar ógvusligar enn det vi langt hava se. Og tog så spurningren hva skjer hvis nu streimaner som renner undan om Føroyar være avvirkar. Ja, hvis det skulle hent at Føroyar vikna inn nere i åndsje, ja, så det mer eller mindre greit at så får vi den kalda streimen inn av okkara hagartil, og vi får några ekvelige dramatiska broytingar og okkara landgrunn, og inn i land i eisen. Som jeg har sagt, så det en spurning som sjølvandi ekvelige avgjørende for okkon, og vi har rundt fylgja vi ut av havstående. Vi har ikke sett noen broytingar enn. Men hvordan ber man seg så at vi hitja etter hvordan vi det i framtiden? Ja, den maten man vanliga gjør innanfor veðurlagsgransking, det det man kallar en klimamodell. En klimamodell, det et veldig telteforrid som bare kører av de største teltene i heimen. Og det flere sånne klimamodell som kører av de store granskingsståndene rundt om i heimen. Og det det man bruker til at som for å si hvordan veðurlaga gjør for å brøytas. Det som jeg her viser, det fra en visetallere grein som kom for noen få måneder siden, i halvt av februar i år. Her og i noen granskere har savnet sammen utslitt fra 36 imiskon klimamodellen, som i middelen de beste som finnes. De sier at gjøren for at hittna i hesar i øldene. Her har man råkna vi at utlatet av CO2 fra mennesken ikke vil avmarska så øyelig nekv, men at det heller ikke vekser så øyelig kraftigt, så mialhøgt CO2 på rett holdt. Som sagt, alle modellen samt om at gjøren hittnar, men tar man så hikker etter hver pastor av en hittnar, så viste det seg at det egentlig store måneder. De fleste av dem, 22 av dem og 36, har en nok så jævna opphiting. Ja, som Julian nevnte, så var det særlig at det arktiske øyne opphita nekk kraftigere enn resten. Men hittar vi at hvordan det i okkara parti av heimen, så var det allikevel alle partene hittar, og vi har som før noen Føroyar hittna 3 sti og i endan av hesar i øldene. Hatt det de fleste sier, så det tjej modell her som har en nega ørvise gongt. Her alt dette øke sånn for Grønland, bei Labradorhavet og Irmingerhavet, det kølna faktisk. Og her ligger Føroyar av marsjen noen vettelen hetta kaldare øke og resten av heimen som hittnar. Så her får man faktisk ikke noen særlige brøyting. Og så det 2 som har en ekvelig dramatiska brøyting hvordan jeg for okkom. Her alt øker mittelen Kanada og norra, faktisk norr om norra kølnar, og en avkølning på 5 grader i Føroyar. Så jeg husker at dette kan virke ikke forvirrende, men dette støvan vi i det. Det ikke nækker som føre for å si hvordan veverleie til okkom for å brøytast. Kunne være optimister og sier, ja, tross alt, her nå 22 av 36 som sier at det for å hittne, så kanskje hatt det som det mest trolige. Og det vel mulig, det vet vi ikke i det. Det jo veldig funnet. Tror jeg stia træt man kunne føre Lennasand og Solasar. Men det kan jo eisen ha avleininger. Hva hender, det har vi faktisk ikke noen mulighet til å vite at det omkant til å være så høyt og noe vi kunne kalle søvligere tog, men vi vet at det imisk fiskeslø som helst vibrert. Takk nebbasiltene. Hon en ekvelig tøyende, selv om hun ser så beskjedende ut, så en ekvelig tøyende pastor av de førske visskipene. Hon grundalega for store pastor av sjåfolkene og sjåken, og for tilgang av torsken. Det en løyenfisker, hon grever seg ned om veteren, ligger atlan veteren nere i sanden og eter ånden, men lever bare å ta i feiten som hun samlet seg om våren og sommaren. Og her nek som bender på at hvis det for heit i sjøen om veteren, så brukar hun mer av feitgømselen, så at hun skal komme opp og begynne omater på et godt liv, da hun deg og ræd. Det ikke godt for sjøfuglen, det ikke godt for torsken. Han jo minne i eta. Han hever her at det problemet at ta i tosker guiter, så vil han helst ikke ha for heitan skjek. Faktisk det så at den første langkroneren et til steg her og hiten og guitingartøyene til torske hakster. Hvis han hiten for 3 sti langer opp, ja, ungen veit, men jeg ikke råkna ved at det var øyelig nekver tosker ta. Så det ikke sikkert at alt så øyelig godt ved å få 3 sti og 3, og takk så oppkjør fisken. Her har vi jo et fekstdøme, vi har makrelen, som kom inn i okkara øke og breidde seg eisene våre vester etter sånn tog som det ble heitar. Kom han tog at sjekkfren hittna i. Ja, hvis vi visste det, så hadde vi kanskje kunnet råkne ut hva han så for å gjøre ta i sjekkfren hittna oppa til meg, hvis han hittna meg. Men spiller dit fiskefrøyngar, vi som arbeider ved makrel, ja, så det nok nærkere som halta til. Men til det som sier, nei, han skiftet tog at det ble så nekver makreler. Stavneren ble nek større, det var ikke plass til det her som det var, tog ble det der seg ut. Hvor ble så stavneren større? Var her kanskje tog at det ble heitere her som man gåtte. Fink der mer å eta, eller var det til at her fink minne å eta her som der var framan undan. Alt dette her spurningar som man faktisk må svære for å kunne si hvordan fer makreleren å brøyta seg hvis sjekkfren brøyta seg på en eller annen måte. Og det jo faktisk ikke så lett. Det ikke lett å være fiskefrøyngar, særlig ikke Føroyar, vil jeg si. Jeg kan si bare at vi ikke fiskefrøyngar. Men det ikke lett, altså, her har finnet makrelen inn i okkara her, og jeg vil gjerne vite hvor, men det jo ikke makrelmål. Så det ingen som kan svære på det. Nedstøvan Ja, det nok så kjeiligt jeg skulle stande her og ha arbeidet vi her og så øyelig når jeg var. Og egentlig bare kunne si at jo, ikke 100, men jeg 95% sikker i at omstøvene er brøytast ekvelig enn resten av hesar i øldene. Men jeg aner ikke hvordan det er å brøytast. Og det det kjeiligaste at det gjør at det ekvelig torrført at planen byrja fyri brøyting. Takk for det.
Ja, Barbara. Takk for Boje. Det får bedre være en løtt chat hvis det kommer onkel spurningar. And I would like Andy and Julian to join me here if in case there will be some questions for you. And Johan, microphone. Here, yes. Fint. Så tid du selv, noen velkomna å sette noen spurningar. Her tvær damer som renner rundt ved mikrofonen. Hvis det var nøyt. Jeg sutjer så et eller oppe, så jeg må holde opp hendene meg, for jeg sutjer om noen hånder opp. Jeg var en hånd oppe, men hun skulle ikke nere. Det var også skriet seg alt. Men sett igjen noen spurningar hvis de har også spør om. Vi tar en låt av boja, hvis det er. Men det tar det sammen. I alle fall ikke bare lade mennene stand her. Jeg sitter nyret nå. Ferdig bare ved mikrofonen hvis han krever også. But I could start. You are scientists, you are experts. When you follow political discussions, political negotiations, the Paris Agreement, and all those things that is going on in the political environment, what does that make you feel? Are you optimistic or are you pessimistic? Julian.
Yeah, I think it's quite a hard question. I remember being asked when, at the time when I think that people who were working on the natural environment first really thought that the signal of environmental change was coming above the noise, the year-to-year noise in the system. And I get that maybe 15 years ago, something like that. And I remember being asked, and several of them, do you come regularly onto the radio and the television to be advocates for climate change and what we were supposed perhaps to do about it and what their suggestions should be. And a number of us actually stood back from this very slightly because the view was in a way that our job as scientists was first to say what is going on, for example, in the polar regions, and what the satellite systems and what the ocean observing systems are really showing about what is going on. And the danger if you start to become an advocate saying we should do this, we should do that, you make yourself vulnerable immediately to criticism by climate change skeptics. So my policy has always to be in the natural world with the smallest error term that we possibly can, and then trying to predict. So what I'm very pleased about in terms of Paris and so on and so on and so on, is that people are taking the baton not only of the information that we provide to them, but making suggestions as to what we should do about it. And I think it's a very important thing. But I do think that advocacy and science are to some extent separate exercises. But I'm delighted to see that politicians and other groups are getting to grips with what we do with the information that the scientific community provides.
Andy, do you have a comment on that?
Well, I think, you know, the role of a technologist or an engineer is, you know, to provide information. And I think that clearly the role of science is to take that information and turn it into something useful for society. The challenge is to break out of the present, to providing that information in particular to the public, and to, you know, empower the public to be knowledgeable enough to help drive some of the policy outside of the political arena. I mean, it's not possible to achieve this in a vacuum, but I think that's, you know, the concept that we're building an information network about the natural environment is potentially heading us in this direction.
I have to mix the languages here, sorry.
Yeah, of course.
Ja, vet du vad med oss för förskon eller
Ja, du svarar bara förskon av det, så. Men du har också för enskon, skulle bara ta det enskon?
Jag hade kanske.
Ja.
So, yes, I think the Paris Agreement is great. I mean, it is a step going the right way. But I don't think we should believe that this is the solution. They say in the Paris Agreement that we aim to not heat the Earth more than 2 degrees. They even have a statement saying we should try to keep the warming below 1.5 degrees. But I think most experts agree that we have already committed to 1.5 degree. Even if we stopped emissions today, the Earth would warm the additional 1.5 degree, simply because the climate system is not in equilibrium. But even if we take the statement that we should keep the warming to 2 degrees, when you then look at what are the individual nations committing to, they were committing to much less than what would be necessary. So if we take what the individual nations say, we will, and even that is not a promise, it's not binding. The Earth will, with the plans that nations now have for their emissions, the Earth will warm regarding if a guy like Trump says, I don't believe this at all, so we just go ahead, then the whole thing goes even more up.
Ja. En mikrofon för en upp här någonstans? Är det någon som har en spårning?
Ja, hej.
Hej.
Jeg har en spurning. Ikke godt Leo, men jeg har en spurning fra livestreaming publikum nå med. And the question is, do you think that our combat against climate change or our society's shift to carbon-free energy can be solved technologically, or will it require fundamental change in how we live? Excuse me. That's a question from our live streaming audience. Did you get the question? Yeah. The question is, can we achieve our combat against climate change by technological means alone, or do we need to shift our ways of living? Or do we require fundamental change in how we live? That's the question from our live streaming audience.
That's a difficult question, of course. I think, you know, it's hard to speak in extremes with such a question. You know, I think realistically it requires technology. You know, can we innovate our way out of some of the challenges that we've been describing in this case. I rather think that it will play a role. Humans are incredibly innovative species, and will we be able to engineer our way out of some of the challenges again that we've described? I think this is a great question. I tend to be optimistic that that's the case. However, I think part of that will involve a change in behavior, which is where the greatest challenge lies. I think the technology is perhaps in many ways a relatively straightforward, no less challenging perhaps, but the behavioral issues coupled with the political challenges. We make jokes about Trump in the United States, but those are real, and I think they are, to a large degree, probably the largest challenges.
I think the clear answer really is that we need to do both, because the technology is taking us forward. There are all sorts of technological things going on right now. In the North Sea, there are experiments with carbon sequestration and so on, which are bearing some fruit. That's an example of a technology. On the other hand, I heard Lord Martin Rees speak at the Davos World Economic Forum last year, warning against the dangers of large-scale geoengineering, because that actually could make matters worse rather than better, because the climate system, as I hope you've got the message today, is a really complicated one. So any sort of geoengineering runs considerable risks, even if we do it with good ends in sight. And so what that means is technologies will deliver some things, but we don't know at the limit what they're going to deliver. And therefore, if we're sensible, we should also try and mitigate through our own behaviours too. And from what we've seen of the wind farms and the Faroes' aims to become carbon-free emitters by 2030, this is the sort of thing that would, I wish, be mirrored in other places. But to become slightly political for a moment, I think that countries like Britain, which has not set as good an example as the Faroes, but has tried to set some kind of example, is unlikely to do any more than it's doing at the moment, given the present political situation. And I think the comments of Andy would imply that the US is even less likely to do that. And when you look at the emerging nations, the emerging powerful and huge nations such as China and India, even if countries like ours set reasonably good, or in the case of the Faroes, very good examples, they turn around and say, we have huge populations. They want to see the kind of lifestyles, or to an extent, the lifestyles that we have. And in fact, when you come to count up who has contributed the most to carbon in the atmosphere, the answer, one, you might guess, is the USA. The answer, two, is actually the United Kingdom, because although we don't contribute much today, we were the cradle of the Industrial Revolution, and in a way we started the whole thing. So it's very easy for China and India to turn around and say, well, we want some different things, and that is part of the global setting in which we are. So what we can do in the West to be good citizens, I think, is very valuable too.
Thank you. Jeg får ikke tvinge bare spurningar. Ja, det kan jeg.
I think one of the problems when you put questions like that to experts, and I think we can call ourselves experts, one on ice, one on technology, and, well, I think of myself as an expert on ocean currents, is that you are asking us questions about something that we are not experts within. So these are just our own personal feelings. And for my sake, I'd say that from what I've read, the technology to solve this is already there. We only need to employ it. And there, perhaps, the most important thing is what the minister said when she started this talk earlier, is that we need, if we want an exaggerated consumerism, where we never think about when we buy a new thing, whether we really need a new thing. This is my personal feeling.
Thank you. Vi får enda med lite løte. Vi enda vi en filmsbrott jag sett. Så vi kan se att uppblåsten till detta kvällte, han kom från Rastavne, 100 by 2030, som sev, skipa fyri her i husen, 7. september i samband med at elfella i fyllt i 4 år. Og jeg hadde virkelig enda hette her vi en film som vi faktisk byrja vi ta, som var framløyder til det høve. Man kan si at mannaten kan spyrja seg selv om hva har vi gjørst vi gjørna, og hva atla vi gjør våre bøtten og kommande i atterligen frametter. And you guys, thank you very much for joining us tonight.
The thousands, they are here in the tens of thousands. Occasionally they shout, Die Mauer muss weg, the wall must go.
You have said it. No, no, no.
For the first time in history, all major economies have come together to accept their responsibility to take action to confront the threat of climate change.
Hopeful, I'm always gonna be hopeful. Hopeful, that's all I am.
Ja, hese bøtten og unge, en så bøtten og unge om allan heim. Det kunne være en god årsøk til at vi talte av, vi strunen imot veðurlagsbroytingum og at vi letja alt la okkara orsku i grøna orskum til jo tvær syr av sommersøk. Som jeg sier, Janne, så det velkommen at være en løtt i husen, takk prat vi granskarna, her okkur godt at få leska seg vi her ute. Og Johan, han vært så finnsammer, han heldre at The Doors skulle fylle jokken ut, hvis han ikke noen Riders on the Storm. Og her er annars et godt kveld.